Have you ever gazed up at the night sky and wondered about the moon? It hangs there, a beacon of light against the backdrop of stars. For millennia, humans have been captivated by its presence. The moon has inspired countless myths, stories, and scientific inquiries. Our moon is more than just a pretty sight. It is Earth's closest celestial companion, and its dance around our planet has profound effects. This dance, known as a lunar orbit, is a delicate balance of forces and motion. Understanding lunar orbits provides insights into fundamental laws of physics. It also helps us appreciate the intricate relationship between Earth and its only natural satellite. Join me as we delve into the fascinating world of lunar orbits. So, what exactly is a lunar orbit? Simply put, it's the path the moon takes as it travels around Earth. Imagine a graceful waltz in space with Earth as the lead and the moon following its lead. This path is not a perfect circle. Instead, it's slightly elliptical, meaning it has a slight oval shape. This means the moon's distance from Earth isn't constant. It has a point where it's closest to Earth, called perigee, and a point where it's farthest, known as apogee. The moon's orbit isn't static either. It's constantly being nudged and pulled by various gravitational forces. These forces, like a gentle tug on a dancer's arm, cause slight variations in the moon's orbital path over time. What keeps the moon in this celestial dance around Earth? It's a question that has fascinated humanity for centuries, from ancient astronomers to modern scientists. The moon's steady orbit around our planet is a delicate balance of forces, a cosmic ballet that has been ongoing for billions of years. The answer, as with most things in the universe, is gravity. This invisible force is the glue that holds the cosmos together, governing the motion of planets, stars, and galaxies. Without gravity, the universe as we know it would be a chaotic, unrecognizable place. Sir Isaac Newton, the brilliant mind who gave us the laws of motion, also unlocked the secrets of gravity. His groundbreaking work in the 17th century laid the foundation for our understanding of how objects interact in space. Newton's insights were revolutionary, changing the way we perceive the universe. Newton's law of universal gravitation states that every object in the universe attracts every other object. This universal attraction is what keeps the planets in their orbits around the sun and moons in their orbits around planets. It's a fundamental principle that applies to all matter, from the smallest particles to the largest celestial bodies. The strength of this attraction depends on two things: the mass of the objects and the distance between them. Larger objects exert a stronger gravitational pull, while the force weakens with increasing distance. This relationship is crucial in determining the dynamics of celestial bodies. The more massive the objects, the stronger the pull. This is why massive stars can hold entire solar systems in their gravitational grip, and why black holes, with their immense mass, have such powerful gravitational fields that not even light can escape. The closer they are, the stronger the attraction. This is why the moon, being relatively close to Earth, is held in a stable orbit. If the moon were farther away, the gravitational pull would be weaker, and its orbit would be less stable. In the case of Earth and the moon, Earth's larger mass exerts a strong gravitational pull on the moon. This pull is what keeps the moon in its orbit, preventing it from drifting off into space. The moon's orbit is a testament to the power of gravitational forces at work. This pull is what keeps the moon from flying off into space. It's a delicate balance, a cosmic dance that has been choreographed by the laws of physics. The moon's orbit is not just a simple path, it's a dynamic interaction of forces that has been fine-tuned over billions of years. Simultaneously, the moon's gravity also tugs on Earth, as we'll explore later. This mutual attraction creates tides and influences the Earth's rotation, showcasing the interconnectedness of celestial bodies. The dance of attraction between Earth and the moon is a beautiful example of the harmony that exists in the universe. The moon's orbital period, or the time it takes to complete one full orbit around Earth, is about 27.3 days. This is known as the sidereal month. However, there's another important cycle, the synodic month, which is about 29.5 days long. The synodic month is what determines the moon's phases. As the moon orbits Earth, the angle at which we see the sunlit portion of the moon changes. This creates the familiar cycle of new moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, last quarter, and waning crescent. These phases have captivated skywatchers for millennia. They've served as a natural calendar, a source of mythology, and a constant reminder of the celestial dance happening above us. Section 5. The ocean's breath tides and the moon. Have you ever been to the beach and witnessed the rhythmic rise and fall of the ocean? This mesmerizing dance of the waves is not just a random occurrence but a fascinating natural phenomenon. These tides, this watery pulse of our planet, are largely driven by the moon's gravitational pull. The moon, our closest celestial neighbor, exerts a powerful force on Earth. As the moon orbits Earth, its gravity tugs on our planet. This gravitational pull is not uniform. It varies depending on the distance between the moon and different parts of Earth. This tug is stronger on the side of Earth facing the moon, causing the water on that side to bulge outward. This bulge is what we observe as a high tide. A similar bulge occurs on the opposite side of Earth due to inertia. Inertia, the tendency of objects to resist changes in their state of motion, causes the water on the far side to also bulge outward. These bulges are what we experience as high tides. When you stand on the shore and see the water reaching its highest point, you are witnessing the direct effect of the moon's gravitational pull. The areas between these bulges experience low tides. During low tide, the water recedes, revealing more of the beach and sometimes exposing marine life that is usually hidden underwater. As Earth rotates, different locations on our planet pass through these tidal bulges, creating the continuous cycle of high and low tides. This rotation ensures that every coastal area experiences both high and low tides, typically twice each day. The interplay between the moon's gravitational pull and Earth's rotation creates a dynamic and ever-changing seascape, a testament to the intricate balance of natural forces at work. Section 6. Not a perfect circle variations in the dance. While we often talk about the moon's orbit as a smooth, predictable path, the reality is a bit more complex. The moon doesn't follow a perfect circular path around Earth. Instead, its orbit is elliptical, meaning it's more like an elongated circle. This elliptical orbit means that the distance between the Earth and the moon changes as the moon travels around our planet. The moon's orbit has slight variations, like a dancer adding subtle flourishes to their routine. These variations are not random, but are influenced by several factors. Just as a dancer might adjust their movements in response to music or the stage, the moon's orbit is influenced by gravitational forces. These variations are caused by the gravitational influence of the Sun and other planets. The Sun's gravity in particular plays a significant role in shaping the moon's path. Additionally, the gravitational pull from other planets, especially the larger ones like Jupiter and Saturn, also affects the moon's orbit, adding layers of complexity to its dance around Earth. One such variation is eccentricity, which refers to how much the moon's elliptical orbit deviates from a perfect circle. When the moon's orbit has higher eccentricity, it means the orbit is more stretched out, making the distance between the Earth and the moon vary more significantly. A higher eccentricity means a more elongated ellipse. This elongation affects not only the distance between the Earth and the moon, but also the speed at which the moon travels along its orbit. When the moon is closer to Earth, it moves faster, and when it's farther away, it moves slower. The moon's eccentricity isn't constant, it varies slightly over time. These variations are influenced by the gravitational interactions with the Sun and other planets, as well as the gravitational pull from Earth itself. Over long periods, these small changes can add up, leading to noticeable differences in the moon's orbit. Another variation is inclination, which is the tilt of the moon's orbital plane with respect to Earth's orbital plane around the Sun. This tilt means that the moon's orbit is not perfectly aligned with the Earth's orbit, adding another layer of complexity to its movement. This inclination is why we don't see solar and lunar eclipses every month. For an eclipse to occur, the Sun, Earth, and Moon must be perfectly aligned. Because of the moon's tilted orbit, this alignment only happens occasionally, making eclipses relatively rare events. Section 7. Lunar influence, from tides to time. The moon's influence on Earth extends beyond tides. Its gravitational pull actually has a slight but measurable effect on Earth's rotation. Over very long periods, this interaction has been gradually slowing down Earth's rotation, making our days slightly longer. Furthermore, the moon plays a crucial role in stabilizing Earth's axial tilt. This tilt is what gives us our seasons. Without the moon's stabilizing presence, Earth's axial tilt could vary chaotically, leading to extreme and unpredictable climate changes. From the rhythm of the tides to the stability of our planet's rotation, the moon's influence is deeply woven into the fabric of life on Earth. Section 8. The future of lunar exploration, a new era. We are on the cusp of a new era of lunar exploration. Space agencies and private companies are planning ambitious missions to the moon, aiming to establish a sustainable human presence on our celestial neighbor. These missions have the potential to revolutionize our understanding of the moon's formation, evolution, and resources. They could also pave the way for future missions to Mars and beyond, using the moon as a stepping stone for deeper space exploration. The moon beckons us to unravel its mysteries and unlock its potential. As we venture further into the cosmos, our nearest celestial neighbor will undoubtedly play a pivotal role in our journey. Section 9. Keep looking up, the universe awaits. The next time you find yourself beneath a starlit sky, take a moment to appreciate the moon. It's more than just a celestial object. It's a testament to the power of gravity, a source of wonder, and a potential gateway to further exploration. Keep questioning, keep exploring, and keep looking up. The universe is vast and full of mysteries waiting to be unveiled. Who knows what other celestial dances await our discovery?